So let's look at this example here. We have three groups of randomly selected students who were given a different dosage of statistioprezol, which is a new drug that supposedly increases a student's ability to perform statistics. Each group was given a statistics pretest. Then two groups were given a certain level of statistioprezol for 2 weeks, while another group took a placebo. Then all groups took a post-test out of 10, and the data is assumed to be from populations that are normally distributed with equal variances. We want to test the claim that the mean test scores are the same for each treatment with a significance level of 0.05. Okay, so here is our data from our sample. We have one group where we took a sample of 4 from the placebo group, 4 from the group that got 10 milligrams of statistioprezol, and another group that got 20 milligrams of statistioprezol. So in each of these, they have the same sample size, 4 in each sample. If we want to compute the mean from each of these samples, right, we could easily do that. So here I'll write down what the mean from each of them is. Here we have a mean of 5.5. Here we have a mean of 7.25. And here we have a mean of 9. And as well, we can also compute the variance from each of these. Which, if you remember, the variance is just now subtracting each of these values from the mean, squaring that difference, and then summing it up for each of them. And then once you do that, then you'll divide by n-1, which in this case would be 3. So after doing that, for this one, we'll have a variance of 4.33 for the first group, 2.25 for the second group, and 0.667 for the third group. Okay, so what you kind of notice here is that the first group has a lot more variation than the other two groups, right? So the first group, we see that 4.33 is telling us essentially how spread out that data is. There's a lot more variation, whereas with the group here, where you have a smaller variance, the numbers are a little bit more consistently close to one another. So what we might conclude is that there is a difference between these three groups, because in particular here, it looks like this group is distinctly different from this group here. In other words, I might be able to, if I were given a random test score, I might be able to distinguish which of these three groups it falls into. Although it might also be tricky, because in this case you've got an 8, in this case you've got a 9 and an 8, and both of those values are in this group as well. So it's very possible that if I got an 8 or a 9, that it could have come from the placebo group or the 10 milligram group. Anyways, so what is the null hypothesis and alternative hypothesis? Remember, the null hypothesis will be that the three means are equal to each other. And the alternative hypothesis is that one of the means is different. So in order to compute the F-score, which we'll do in the next slide, we'll need to know these two things. Remember, this is going to be what we're calling the mean square error, and this is going to be the mean square factor. Oh, I'm sorry, I got that backwards. This is the mean square factor, and this is the mean square error. And if you remember, really what this is n, the sample size n, times the variance of the x bars. So that's kind of what this notation represents here. It's the variance of the x bars. So we have the 3 x bars here. So we can look for, we're going to do n times the variance of those three values, 5.5, 7.25, and 9. And let's see, in this case, if you do that, it'll be 4 times, when you compute the variance between these three numbers, in other words, take the mean of the three numbers, subtract each of the numbers from the mean, square the difference, and divide by n minus 1. In this case, there's 3, so it would be 2. When you do that, you get something around 3.0625. So that would be what we get here for the variance between the samples. So 12.25 when we compute that. For the other part, where it's the variance within the samples, what we're really taking there is the mean of the variances. In other words, the mean of the s-squareds. So, or not means, but just a single mean. So it's the mean of the variances. Here we're taking the variance of the means, here we're taking the mean of the variances. So now we'll look at these three values here and just take the mean of these three numbers. So you can add them up and divide by 3. Okay. And that'll give us something around 2.416. That'll be the MS error. So now to compute the f-score, we're going to divide this number by this number. Okay, so as we computed in the previous slide, we found here for the mean squares error was 12.25. And then dividing by that was the mean squares factor. This is the mean squares error that goes down here, 2.416. And when we divide them, we get something about 5.0689, which corresponds to the f-score here that we're going to compute the area of the right tail. So area to the right of that f-score on our f distribution here. So remember, this is the f distribution. And remember, this is kind of telling us a couple of things. This is in the top, it was what we call the mean square factor, which was the variance between the samples. And then below it was the variance within the samples. So if we imagine we have a lot of variation between the samples, then we're going to have a higher value up here. And if each of the samples, individual samples, have a smaller variation within it, then we're going to divide by a smaller number, and so that'll make this value bigger as well. So that kind of helps us distinguish between the different groups. If, for instance, we have groups that have bigger variances between them and smaller variances within them, it'll be easier to distinguish between them. So for the p-value, we're going to use FCDF to find the area under the f distribution. Now we'll enter the lower and the upper, where we got for the lower 5.0689 was the f-score that we computed. Upper, we can use 1E99, and then we'll need the the degrees of freedom of the factor, which was 2. How did we get that? That's k minus 1, where k is the number of samples. In this case we had 3 samples, so it'll be 3 minus 1, or 2. And then for the degrees of freedom of our error, it'll be, in this case, it'll be 9. And remember, how did we get that? That'll be k times n minus 1. In this case, k was how many samples? We're doing 3 samples, and n was the number of the size of each sample. In this case, we had 4 in each sample, so that'll be 3 for n minus 1. So it'll be 3 times 3 is 9. And let's see, when we compute here, we get something around 0.03354. So that'll be the area of our region here, the p-value. And now comparing that with our significance level of 0.05, it looks like here our p-value is smaller. So since our p-value here .03354 was less than our significance level of 0.05, we're going to be able to reject the null hypothesis. And so in this case, there's evidence to support the rejection of our null hypothesis. That the 3 means of each of the populations were the same. So in other words, one of the means, at least one of the means, is different. So as I mentioned before, perhaps a shortcut or a much simpler way of computing the f-score and the p-value will be to use the ANOVA function on our calculator. And before we go to the ANOVA function, what you're going to want to do is first enter each of our sample data into a separate list. So for instance, if I'm comparing 3 groups, you know, I would for instance want to do L1, L2, and L3. For instance, so I'm entering sample data into each of these 3 different lists, and then once there, then I can do ANOVA. So I'll go to stat test, and it's all the way at the bottom is ANOVA, and then enter L1, L2, L3, separated by commas. So making sure to use commas there to separate between the separate lists. And once you do that, then it'll output both the f-score and the p-value. And by the way, it'll also give you a whole bunch of other stuff. It'll give you all the information about the factor, for instance, the degrees of freedom, the sum of the squares and the mean squares. And then for the error, the same thing, the degrees of freedom, the sum of the squares, and the mean of the squares. So that'll be useful if you need that separate information, but the main thing that we're going to be using will be just the f-score and the p-value.